because ultimately the end goal is to what? Find a solution. For this case, solutions mean where it crosses the x-axis, right? Those are going to be our solutions. So when we don't know, or if we're on the ACT or we're taking another test and you're like, how can I best guess? We've learned to break apart our formula, our equations, so that we can best guess where we're at. So for the top one here, we start out where it's got our highest degree is what? Can you see on that one? 4. The highest degree is 4. And our A value is what number? -3. So this A value is the one that controls the whole graph, correct?
Yeah.
So it's going to face what direction? Down. So we already know that the end of it is going to be going down. Okay. Then what's the next number that we look at? The exponent of the highest exponent, right? So this is the degree. It's called the degree of your polynomial. Okay, so this exponent is 4, and whenever it was 4, it falls into what category? Odd or even? So if it's even, it does what?
Faces the same direction.
It has to face the exact same direction. Okay, so we already know the ends have to go like that. So then we'll check it. Does it? Do the ends kind of look like our graph there? Yes. So we've got bumps in here. Our degree also tells us something very important about the solutions. What does it tell us? What did we learn last week? The degree tells us about the solutions. Okay, it can have up to 4. Does it have to have the number of solutions as the degree says? No, but the maximum number of solutions that it could have is equivalent to the degree. So my degree is 4, so the maximum solutions it could have is 4. And let's look at this one. It has 1, 2, 3, 4. 4 solutions in that case. All right, so on this one, even though it doesn't have all of these parts in the middle, the graph should look almost just like what we had, correct? It is. It's still facing down. They're in the same direction because it's even. It just didn't have all the bumps in the middle. So what we can tell is that when we add these extra squares and cubes and things, it's going to start, those are places where your graph turns. Okay? So when we didn't have this extra, we basically just had a big quadratic in disguise, right? Because we could rewrite this, as something squared, like the square root of 3x, the whole thing squared on it. Okay, so let's look at this one. What's our A value here? -1, so our end does what? Faces down. What's our degree of the polynomial? 3. So this type of equation would be called a what? Cubic. Excellent. Would be called a cubic. Okay, so we know it faces down. We know it's called a cubic. And what about the other side? It's opposite, so because it was odd, so it's going to go up. Correct? So let's double check that one. There we go. Okay, so we're seeing that our graphs are matching what we're saying we think they should. Okay? And we only have one extra term in the middle, so we have one turn of our graph. It says it has the opportunity of having 3 solutions, but we just have one solution. Now, if this graph were changed in such a way that this one turn made it above the x-axis and went down, how many solutions would it have? 3. So do we see how it could have 3? And that's dependent upon those numbers in the middle. So the next one, what should it look like? X cubed minus 3x minus 1. So what type of equation is it?
Cubic.
It's a cubic. Okay, what is the A value?
1.
1.
The A value is a 1. Positive or negative?
Positive.
Positive. So the end of the graph should do what?
Face up.
It should go up. What is our index? Or sorry, our degree. What's the highest degree?
3.
3, which is odd, so it
Faces down.
goes down. Okay. Let's look at this one. All right. And then we have one turn in the middle. Correct? And it has how many solutions?
3.
1, 2, 3. Okay, so let's look at this last one. Y equals 2x to the 6th. What should the end look like? Positive. Okay, great, Joshua. And then where should it start? It's a 6. Does it really matter?
No.
Is 6 odd or even?
Even.
It's even. So if it's even, it has to be the same. So it's coming from that direction as well. It could have how many solutions?
6.
6. It could have 6 solutions. Okay, but it doesn't on this one. Just goes right along the end because it doesn't have any of the extras. So again, this is a good example, some good practice. We're switching over, okay? Now, let's go back. Okay. So before we get started, when I'm figuring this, everybody stand up, put your arms over your head. Everyone came from English. English is like my nappy class. So move around.
Sorry, we were looking for keys.
Oh, you're fine.
Trying to
You're
go
not-
through your stuff.
So move around, get your blood flowing, and then we'll get our brains engaged for something else. So feel free to stretch and everything, and I will figure out which slide we need to be on. Okay. You guys feel a little bit better? Move around a bit? All right, so last week we spent a lot of time looking at how to evaluate our equations, and we skipped some of the specifics on how we get there and how we undo from getting there, okay? And so we're going to go back and address those and then move forward with that. Okay, so initially, when we're looking at our polynomials, when we addressed this, that it has to have a variable base with a real number for your exponent. So in this case, I've got 3 raised to the x. This is not going to be considered a function. In this case, we had a -1 exponent, which would put it in the denominator, so it's not a function either. Okay? And when we solved them way back in the day, when we changed y and we said f of x instead, it's just our instruction template, correct? So when we say f of 3, that means everywhere I see x, I'm going to plug in 3. So just as before, we were able to take our number that we're solving for, in this case, x equals 3, is what we're saying. So I could have written x equals 3. If I'm saying x equals 3 with a polynomial, that means 3 is a what? 3 would be a solution, correct? So if we've got our graph, and I'm saying x is equal to 3, that's a part where we've crossed the x-axis. So 3 is a solution to the equation here, and then we just plug it in everywhere we're going. So when x equals 3, in this case, y equals 98. Okay, what would y need to be equal to for x equal 3 to really be a solution to that graph? Y would need to come out to what?
0.
0. It would need to come out to 0. Excellent. So when we get into higher degrees, we can still substitute these numbers in, just like this. All right? It just starts getting complicated, right? We've got lots along the way. One of the number one things that ends up being complicated is if you have a negative number in front of here. So if I had a negative 2x to the fourth and I'm plugging it in, often this part gets to be included in the exponent. And so then you're like, well, now I've cubed a negative and I really shouldn't have it. The negative was up front and it wasn't part of that. You know, so we can get complicated as we start getting more. So I mean, if you had a degree of 6 and you have 5 more terms after this, you've got a lot of things that you can plug in. A lot of places where you could make a little error, correct? So instead, there's a shortcut way to do this, okay? And it's called synthetic substitution. And the reason it's called synthetic is it means it's like it's another way to get the same thing, but it's not like the real long way, okay? So I just like to use it as a shortcut. So what we see here is that we did f of 3 and we end up with 98. So we're going to see if we get 98 in the same way. Right. When we do synthetic substitution, all we're doing is we're taking our original equation and instead of plugging our 3 into all of the x places and actually working out all of the x parts, we're going to get rid of all of the x parts. Okay? So to do that, we're only working with the coefficients. Now, the trick is that when we work with the coefficients and we start with the highest degree, we have to have a space for every single part. So just as if we were having, if we were doing tens units, I would have ones, tens, 100s, 1,000. You know, if you're plugging in a number, you have to have something in each of those spots. So in this case, whatever our degree ends up being as we go across, if we start with x to the fourth, then we have to work our way down. So we have to have x cubed, x squared, x, and then our constant. Right? So wherever you start at the top, you have to have a space for each one, working all the way down. So let's look at this one. We've got 2x to the fourth plus 8x squared plus 5x minus 7. If I have to have a row for each one, which variable degree is missing? Cubed. Correct. X cubed. So we went from 4 to 2. So in that x cubed spot, we have to write a 0. So what we do is initially you start and we're going to copy down all of the coefficients. So in this case, my coefficient for 4 is 2. My coefficient for x cubed is 0. It doesn't exist. Correct? Then I've got negative 8, 5, and 7. And you have to have a constant. If I had no constant and it ended here, what number would I put for my constant? 0. You'd also put 0 for your constant, right? So this is what it looks like initially. We've got to have all of our little rows. I'm going to leave this up here so that we can see where everything lines up. Now, when we pull the coefficients down, we're going to ask ourselves the question, what is x? In this case, they tell us that x equals what? 3. All right? X equals 3. Now, if I had this, x minus 2 equals 0, what is x? X would be positive 2. Okay? So the question that we're putting in this box is what is x? This is what we're solving for. So if they tell you the number outright, you get to put the number in there. If they tell you the number in some sort of little binomial like this, you might have to solve for x first before you know what number to put in. Okay? Now, here are the steps. We are going to multiply, add, and repeat. Is what we do over and over. Right? And to think about that, if we were putting this in here, we would be multiplying these numbers together. Okay? So this first 2 just drops down. So it goes down here in this answer. So your answers are going to end up being down here at the bottom. So I drop my 2 down, and now I'm going to multiply. 3 times 2
6.
is 6. So I put it up top. That's why I have the little arrows. And then we're going to add them together. 0 plus 6 is 6. Now we're just going to repeat that. 3 times 6 is 18. I'm going to add them together and get 10. 3 times 10 is 30. We're going to add these together and get 35. 3 times 35 is what? 105? Oh, that should be negative 7, right? And 105 minus 7 gives me 98. Okay, did I get the same answer? Oh, wrong way. Did I get the same answer? 98. Okay? So we're able to take just the coefficients without actually multiplying out all of the variable portions and end up with the same solution using the synthetic substitution. This is going to be important as we move through in a little bit when we talk about polynomial long division. We're using the exact same thing. This is why, okay? So, for example, on this one, you could have something that looks really kind of messy. Okay, we start with our highest degree of 3, so we need to make sure we have something in every spot. We've got 3, 2, 1, and a constant. Are we going to have to add any extra zeros into it? No. So we would just use our coefficients all the way across, and they are asking when, in this case, time equals 100. So we're putting in 100 for our x value. Now that would make it really complicated if I actually began to plug in that. We would end up with a lot of exponents, correct? Because now I've got 0.000015 times 100 to the third. So I'm going to have 1, 2, 3, 4, 5, 6 zeros and multiplying. So we can see how it's like, oh, this would be a shorter cut way than adding all it in. So we're going to drop down, multiply. It simply moves our 2 decimals over. And then we add together. Drop down, multiply. In this case, because when I added, I ended up with a negative 0.0019. Do not lose your negative sign. 100. Here we're just moving that over 2 decimal places, but I've got a negative 0.19. So we're adding them together again. We're moving it up. We're adding it again. Our answer is 11.3 in that case. All right, so let's look at this one. F of 2. We start with a degree of 5. So I need a space for 5, 4, 3, 2, 1, and 0. I have a 5, I have 2, I have a 1, I didn't have a constant. So we've had to place zeros in the spot for x to the 4th and x cubed, and we have to place a 0 in the spot for the constant. Okay? Do we see why we started with all these zeros? Right? So we drop, multiply, and add. When we move all the way across, we would get our answer. F of 2, in this case, what we would write is F of 2 is equal to 90. So as a coordinate, how would I write that? What is this telling me?
2.
When x equals 2, y equals 90. Remember, the information that we get, the numbers, always tell us something. There's a sentence that we can make out of that. So when x equals 2, y equals 90 on this graph. Okay? What direction should that graph face?
Up.
Should face up at the end. Okay? And where does it start?
At the bottom.
Starts down because it's x to the 5th, right? So it's going to do something and maybe do like that. And when x equals 2, this graph is going to be at 90 up here. Right? Okay, So we already addressed in behavior. So we did last week. Okay. So let's do another, I'm gonna pull this up. Let's do a couple other synthetic substitutions. Let's work it out. If I'm given f of x and they say when x equals -3. Right? So in this case, I would replace my x with a -3. And when I'm starting across, I need a fourth, third, squared, 1, and a constant. So what numbers do I put in here? What's my first number?
-1,
-1,
1,
1,
0,
okay,
-1,
-1, and 1, okay? And I'm looking for x equals -3. Okay? So I'm going to put -3 in my little box. The first one we're going to drop down, -1. -3 times -1.
3.
Okay, and we add these together and get 4. -3 times 4. Add them together. -12. -3 times 12. 36. Add those together and we're going to get 35. 3 times 35 we already learned was 105? But it's negative. So I have -104. Okay? So when x equals -3, y equals -104. This could be rewritten as a coordinate of x equal to -3 and y equal to -104. That make sense? Okay. Anyone want to come work one on the board for a piece of candy? Or we want to move on? Any questions about this? You have homework in these if you didn't already do them.
Is it worth it?
Is it worth it?
Mm-hmm.
For what?
I think,
I don't know. That's your decision.
yeah, this is
Okay. Not today.
not too bad.
Today, at the end of the day. Okay. So operations in 6.3. I know a lot of you guys went ahead and did this assignment. I'm going to just go over it just in case you didn't already do this assignment. Or if you had questions, or if you're like, I kind of went through it and I wrote down the answers and I'm not sure exactly how I got there. So operations with polynomials are exactly the same. Doesn't matter how high the degree gets. We do the same process. You know, we're using PEMDAS and the rules still apply. You can only add like terms with it. So initially in this, if you have a plus or a minus with them, we already talked about multiplication and how we have to distribute it out to each one. In this case, we're looking at plus or minus. So we have to add like terms. For these top two, that means the x cubed families have to add with x cubed families. You can't add anything that's not a like term. So in this case, I had 3 of the x cubes on one side and 1 on the other side. So now I have 4 of them. If I had a term, if this one was 3x cubed plus x squared, and I had x cubed plus 8, and I'm adding these together, I could add my cubed terms, but in this case I don't have a squared term over here, so he would just stay, right? So just as before. So we do have 2 squared terms. We can add them together. Remember, the sign must travel with the number. Our signs no longer are just sitting out in space. They're actually a part of that value there. So I've got a -10 and a 2, so I've got a -8. I don't have an x over here on the right side. We just have one on the left, so he just stays. And then I had 8 and -7 gives me 1. Okay? So if we were adding them together, here's what we get. If we subtracted, we do the same thing. We're looking only at the individual terms. We'd end up with a different answer. Okay? Any questions for adding and subtracting like terms for polynomials? Pretty straightforward, exactly what it was before. Okay? If we are distributing them, in this case, the thing that we end up getting, we're used to distributing one number, correct? If I have 2 times 2x plus 3, what I'm going to do? 2 times the first term gives me 4x. 2 times the last term gives me 6. Okay. When we distribute, the rule that we're saying, even though we've only been using 1, is that we're taking that number and we're giving it to each of the terms. Well, when we start having binomials up front, instead of just a singular one, so in this case we have x minus 3, and we're multiplying the whole thing times x squared plus 2x plus 4, negative x squared there, okay? There's a couple different ways. Right here I've shown it vertically in this case, so we've shown horizontally. We're going to work them out together, okay? So if I had something vertical, if I had 125 times 12, when we learned this in elementary school, we learned that we deal with the 2 first and multiply it, correct? And then we deal with the 1. So in this case, I would do 2 times 5, then 2 times 2 plus the 1, then my 2 across. We drop and carry a space there, and then we're going to multiply again. So we had what we learned in elementary is the same thing. You just don't realize what you're doing. So basically we had, this was the solution when we multiplied the 2 for the 1's place, and we have another solution when we multiply the 1 in the 10's place, and then we're adding like terms. In this case, we're adding the 1 values. Now we're adding the 10's. We're adding the 100s. We're adding the 1000s. So we're still only adding like families. So using that same exact format, we're going to put our bigger number, our bigger polynomial up top. We're going to put our smaller one on the bottom, and we're going to work it just like we would if this was 125 times 12. We're going to take our very first term that's in our 1's place here, so we've got -3, and we would multiply it times each of the terms. And I'm going to have a solution that comes from my -3 being multiplied. Then we're going to take our first term, the x, and we're going to multiply it. If you notice, we had an empty holder spot, correct? Because when we were multiplying with regular numbers, they always just say, put that 0 there, hold it. Because what we're technically doing is combining like terms. So when I do my very first term, 4 times x, I get 4x. I have to put it in the x column. It can't go over here with our constant. So again, we're lining everything up with like terms. They just don't teach you that when you're in 4th grade doing, bigger multiplication. And so again, I have an entire trinomial here that comes from my x value, and then we're going to simply add like terms and get a solution. Okay? If we have it horizontally, we do the same thing. And usually we just start from the beginning and then work our way back. So we're going to take our x, and it has to be distributed towards every single thing. So x times -x squared gives us -x cubed. X times 2x, we've got 2x squared. X times 4, and we have 4x. So we should have the same solution from whenever we multiply the x across both sides. Now we have to multiply the other one. This is the number one error that I see whenever we're distributing out with binomials. Remember, the sign must go with the number. So in this case, we did our x. Now my next one is -3. So we are actually distributing out -3 to each of these terms. So I've got -3 times x squared is going to give me a positive 3x squared. And I've got a -6x and a -12. And again, we should end up with the same solution. We add our like terms together and we get our polynomial at the end. Okay, so horizontal version, vertical version when we're multiplying them out. Okay, certain special patterns that are really valuable to cut down on a lot of time of what you have is when we were doing the binomials, remember we had difference of squares? It was super easy. If you saw a squared minus 25, you knew that you could quickly factor that, right? So it's going to be +5 and -5. So when we see things, we're like, oh, I don't even have to think about how to factor that. I can quickly factor it out. So we were able to do that with our binomials. Well, there are special things for trinomials that we can also do that will always have the same form when we factor. So as you're having a factor, what's the point of factoring? We need to factor so that we can find a solution, right? So it's not just for fun, we're actually just trying to find something, right? So there was perfect squares, difference of squares, there were perfect squares binomials, and so with a cube, this is the new one, we have an addition and a subtraction, both with cube forms, okay? So one thing to notice is this is on how do we get it in the first place, and then we're going to look at undoing some of it. So if you have numbers and the entire binomial is cubed, it will always turn into this format. And I wrote your A exponents go down and your B exponents go up. So we're going to start with our highest degree. So we start with a 3, and then you could just write them in. 3, 2, 1, and then I'm not going to have one, right? Because A to the 0 is, what was that exponent rule? Any variable to a 0 is, any variable to 0 is the number 1. Okay, so we don't need a coefficient of 1, correct? Then with B, you could start at the end and you're going to work your way back up. 3, 2, 1, 0. B to the 0 is 1, so he doesn't exist there. And then the middle numbers are both 3. So it makes it easy because you're like, I've got cubes. So I'm going to start with a cube. I'm going to have 3's for both of them. This one I've got a squared b, and this one is ab squared. So the squared term is different. Again, because we started with the a and we worked our way down. Here we started with b at 3 and we worked our way backwards. And if you notice, the sign has to match. So this is a plus b. And so we start out with a plus and we end with a plus. Right? Now, if it's negative, the rule still applies. So I start out with a, and I'm going to go 3, 2, 1, 0. I'm going to start backwards with b, go 3, 2, 1, 0. I have 3's in the middle. The thing that's important about the sign, same thing. Whatever my sign is, the first and the last are the same exact sign. Okay? Your middle one is always positive. So those are just tricks of, we can actually multiply it out. If we multiplied it, it looks like this, correct? So we would have to multiply 2 of them first and get a squared plus 2ab plus b squared, right? And then have this whole thing times it again, and we're going to distribute out. So we could do this, and you can actually work it out, or you memorize the pattern, and this is a shortcut way for it. So either way, you're welcome to work it out, as long as you don't miss any of the distribution, or you can memorize the pattern of it. So if we're starting with something cubed, we know how to get there. So what do we do? I don't know where that one is. So then we'll also learn how to undo them. Okay? So what if, when we knew that we had a squared minus 25, we were able to quickly factor it. What if we have a cubed minus, I wonder what did I do? A cubed minus 8. Okay, so I already know, if I see a squared minus 25, I immediately know how to factor that. That's a difference of cubes. It's going to be plus or minus. Is there a trick that we can learn for a difference of cubes? If we had a difference of squares, could we have a difference of cubes? Yes. So, there's a sum of cubes and a difference of cubes. So this is the thing that is different. When we had a sum of squares, it didn't factor a certain way. It was only special if it was a difference of squares. For cubes, there's actually a special, it works for both addition and the subtraction of it. So in this case, this does not look like our A and our B values cubed all together. Okay? These are not the same. This is our first value is cubed, and we are either adding or subtracting our second value. How could I rewrite this so that they're both cubed? 8 is 2 cubed. Okay. It is going to be valuable for you to rewrite your difference or sum of cubes as the actual numbers cubed, because we use their bases as part of the solution. Okay, so when it's in this form, the only numbers that you need are A and 2. So we've gotten rid of the 8 because then that's not confusing us in that way. Okay? So this tells us the special pattern. I'm going to work through it and show you how I like to work with it, okay? So sums and difference of cubes, it always factors as one binomial and then one trinomial. So your answer will always be a binomial and then a trinomial. So you're going to have a binomial first, you're going to have a trinomial second. Right? So the very first thing that you need to do is write out spots for a binomial and write out spots for a trinomial. Okay? The next thing that we do is that we take our terms that are cubed and we're just going to start putting them into places. Okay? So in the first binomial, it's just those two terms. So in this case, I've got a cubed minus 2 cubed, so I'm going to put an a and I'm going to put a 2. Okay? I usually take and put my a in all the same spots, and I'll show you that in a minute, and then put my 2 in all of its spots. So then on the second one, I basically have 3 spots, right? Because I've got this trinomial. So I'm going to put my a again. My a goes in 3 places because it's cubed. A goes in the first one, first here, and it goes here. And then my b goes in my b spot. It's going to go here. Oh, that's a 2. And it's going to go there again. So this is the skeleton of where we start. We have our binomial, we have our trinomial. Our trinomial is a squared term. Our n terms are squared. So whatever we're putting in is going to be squared. Right? So now I've got an a and a 2, an a squared, an a and a 2, and then a 2 squared. Okay? This is why it's important to rewrite our b term as the actual cubed term. Okay, so here's the skeleton part of it. So as you can see up here, I have x cubed plus 8, so I rewrote it. So I've got my x, and then my x and my x. And those first spots that I've got my 2, I'm going to put it in the binomial spot, in the middle, and then at the end. Right? Now, the sign now follows down. So the sign of the binomial always matches the sign of your initial. equation. So if it was x cubed plus 8, then the binomial sign must be plus. So in this case, our initial sign is negative, so the binomial sign must be negative. Okay? The signs must match. So your initial addition or subtraction of cubes must match your binomial sign. Okay? The trinomial sign must always be the opposite. So if I start with addition, my first sign will be subtraction. If I start with subtraction, my first sign will be addition. And the last sign is always positive. Okay? So the two signs that you're worried about, the one of the binomial and the first one of the trinomial, the binomial must match, the trinomial must be opposite. Right, so we have all of our skeleton parts in it, and then we just factor out. In this case, a squared stays a squared. We typically like to put the coefficient in front of the variable, so we're going to make it 2a, and then 2 squared is actually 4. So at the end, you'll have to work out your numbers again. I think I have a couple of extras. Okay, so let's work this one. Remove my spaces here. Let's work this one together. The first thing that we're going to do when given x cubed minus 27 is to rewrite it as a difference of cubes. So I've got x cubed minus, and 27 is what? I have it up there. 3 cubed. Okay. So now we have our bases. X and 3. Okay. This is me. I'm working my first one. My binomial has an x and it has a 3 in it. I'm going to just copy down my numbers. My trinomial, I have an x in the first spot and an x in the second spot. Then for my 3, I have a 3 in the second spot and a 3 in my end spot. My first and my last terms are squared. Okay, so now I'm getting all the skeleton in. So now I've got to figure out my signs. The sign of my original is negative. So the sign of my binomial is negative. So the first sign of my trinomial is positive, and my last sign is positive, always positive. So if I'm rewriting, I've got x minus 3 times x squared plus 3x plus, I'm going to work that out, 3 squared, 9.
So is the middle term 3x or x?
It doesn't matter. No, that's not x to the third. It's not cubed. These are just 2 spots. They're multiplied together.
So it can be rewritten as the...
Yeah, I typically, for me, because whenever I'm dropping them in, I'm putting them all in order. So I'll do x, 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 and then I do 3, 3, 3. I'm just dropping my numbers into the right spaces. So what that does is it typically puts my variable first and my variable first, my number second, because I'm doing it according to my variable and then my number, my constant. But we don't like to say x times 3. We like to write it as 3x. It's the same thing. I'm just using the commutative property. Since they're multiplied, they can be written in whatever order. All right? So is that what we got? X minus 3, x squared plus 3x plus 9? Yep. Worked it out perfectly. Okay? If we were working this one, okay, so we're starting with our x. In this case, we started with x to the 6th plus 125. Okay? This does not look like an addition or subtraction of cubes, correct? But can I rewrite it as I'm like, well, I've got 6, that's 3 is a factor of 6, and 125 is 5 cubed. So you can rewrite, I rewrote it as x squared cubed, because what's our rule? A power raised to a power, you do what? What was that exponent rule? You multiply. Excellent, Joshua. A power raised to the power, we multiply them. So x squared to the third, and then I've got 5 cubed. So my base, what is my a base?
A squared.
Is actually x squared. So I'm going to plug it in. I've got x squared, x squared, x squared. And this whole first one is squared. This whole last one is squared. Okay? So I'm plugging in my a to all the spaces. The first part of the binomial and the first two of the trinomial. Okay? Now my b base is 5. So let's plug it in. 5, 5, and 5. Right? So my sign is what? Addition. So the sign of the binomial is addition. The sign of the trinomial is
Minus.
subtraction. And the last sign is positive. So now we're just going to clean it up. We've got x squared plus 5. And now here I've got an exponent raised to an exponent. X to the fourth minus, put that one up there, 5x squared plus 5 squared is 25. All right? So the first term is squared, the last term is squared. I like to use my little parentheses whenever I'm putting in, just that way I don't lose anything, especially if we already had an exponent there. Okay. Now in this case, once you get down to here, remember, the goal is we're trying to find a solution. So this is a way that we're helping to factor. We're finally getting down to a solution. We've taken it from an addition and subtraction of cubes. We've found some factors. It's like, what's the whole point? Why are we doing this? So we're going from x to the 6 plus 125. What are the solutions of this? Well, we can either factor it. We can't use the quadratic formula for it. We're not going to use completing the squares. The goal is to find a solution, so we've got to find factors. So we get down here and we have these factors. In this case, if we could continue factoring, we would just keep factoring down to find a solution. This is a quadratic in disguise. Why would I say this trinomial here is a quadratic in disguise? So we know a quadratic is x squared plus x plus constant or whatever, right? What if I rewrote this as x squared squared minus 5 x squared plus 25? So I actually have 2, 1, 0. It's just my variable is actually x squared instead of a. Do we see how? So when we have something that's like a fourth or something that's a multiple of 2, you always want to look and see if it's just a quadratic in disguise. And that your actual variable might be a variable with an exponent. So at this point, we could use the quadratic formula for this one and get down. We could use roots to find this one. X is going to be plus or minus the square root of -5. So imaginary. So is it going to have any spots that cross the x-axis? No? Right, so remember, we're looking to be able to find a solution. Find that when y equals 0, x equals what? All right. So in this one, we start out with 16u to the 5th minus 250u squared. We're in a section that's talking about difference of cubes, so I'm going to say, hey, is there a way I can make this a difference of cubes? So in the first part of this, and this was a section on your test as well, we need to factor something out, right? Can we factor, what do they both have in common? They both have a 2, a factor of 2, and u squared in common. So we could factor that out. When we factor it out, does it disappear? No, if we've got it equal to something and we're factoring both sides, then it can disappear. In this case, there's no equal sign, so we can't disappear. It can't go away. It just has to stay up front. So when I factor out the 2u squared, I end up with 8u cubed minus 125. Now this looks like a difference of cubes. Right? My base is 2u cubed. Why did I put it inside of parentheses here? You can tell me why I put it in parentheses.
To keep it all straight.
To keep it straight, and because I need to distribute this exponent to both of them, correct? Because if I said 2u cubed, does that equal 8u cubed? No, because the exponent is only for the u at this place. So I wanted the 2 to also be cubed. I could write it like that, 2 cubed times u cubed. That's really kind of messy. So we use our parentheses so that we know we are actually distributing that exponent to both of the terms. I've rewritten 125 as 5. So what does that look like? We leave our 2u. We have a binomial and a trinomial. What goes in the binomial? What's the first term of the binomial? Jace, what's that first term?
8u cubed. Oh, which we
For the binomial. So we're looking, so we know it's a difference of cubes. So it breaks up into a binomial and it breaks up into a trinomial. Right? So basically I have a cubed minus b cubed. What is my a value?
Oh, 2.
2 what?
U.
2u. So I'm going to put 2u in that first spot. 2u over here in my trinomial. The whole thing is squared, and then 2u again for my second spot. Right? What's my b term? Eden, what's my b term? 5. So 5 goes in that second spot. 5 goes in my second spot over here, and then 5 goes in the end. And it's squared. Okay. What's my sign? What's the sign of the binomial?
Negative.
Yep, so the sign of the original is negative, so the sign of my binomial is negative. That means the sign of my trinomial is positive, and my last sign is always positive, okay? So now we've broken it out even more. So now we have 2u squared times 2u minus 5. If I'm working this one out, this is why it's important to have our parentheses around it. 2u, the whole thing is squared, so what is my number? Exponent rules. This 2 is distributed to both of them. So it's 4u squared plus 10u plus 25. Right? And if we can factor this one more, we would. We would factor this one more. It's just a regular quadratic. And then we ask ourselves, what are the solutions? Remember, the solutions are when y equals 0. So to find when y equals 0, that means some part of this equation must be 0, correct? So we set each part equal to 0. So I could say 2u squared equals 0. 2u minus 5 equals 0. I don't know if you can factor that more. In this case, we might just use the quadratic formula to find solutions for that one. In this case, u equals 0, right? In this one, u equals 5 halves. And then we would also have solutions that come from here. Right? Because I started with 5, that means I could have 5 solutions. So I could have 1, and I already have 2. 1, 2, 3, 4. Each of these would give me a solution, correct? Since this is squared, that's technically plus or minus, but plus or minus 0 is the same. So is that my 5 solutions? 1, 2, 3, 4, 5. There's So that's how we're working back to get our 5 solutions. We started with 5, we would factor it out and have 5 different opportunities to find it. A lot of times, your factor parts might not give you a solution. They might be the imaginary parts, and that just means it's turning, like we were looking on the graph, it's turning in places where it actually doesn't cross the x-axis for it. Right? So again, that one worked out. Okay. Sometimes if we look at a whole list of a polynomial and it doesn't look like a difference of cubes, it might need to just be grouped together and have things pulled out. So in this case, I have 4 terms and I'm grouping the first terms. I underline those with red. I grouped my second terms, underline them with green, making sure to not lose our negative sign, right? So in the first 2, between x cubed and negative x squared, I can say they both have an x squared in common. I can factor that out, and I'm left with x minus 2. It is important to put it in parentheses. The parentheses tell us that this x squared goes to both of them. That's how we get back to the beginning. Okay? Now, out of the second one, negative 9x plus 18, here's the hint. If you factored the first ones, and you got a binomial, you want your second binomial to match the first binomial. Because the whole point is to continue to get to something where you have another thing that's exactly the same that you're factoring out again, because that's what you're really doing. Remember we had talked about that, like you have to pull out the same thing. So on this back end, with the red side, I got x squared times x minus 2. For me to go anywhere further with this on the green side, I have to either end up with an x squared or x minus 2, because I'm trying to pull something out of both of them. So since I know I'm not getting an x squared out of it, maybe I could turn this and get an x minus 2. That means if I just factored out a positive 9, I would have negative x here and a plus 2. And that doesn't give me something that matches. So that doesn't help me. Okay? So we're going to factor out a negative 9 and get x minus 2. Well, now I have 2 parts that match. So technically what we're doing is we're now factoring out x minus 2, and what we're left with is x squared minus 9. Right? X minus 2 is as far as it can go. X squared minus 9, when we look at that, we go, light bulb, this is a difference of squares. Right? I know how to factor a difference of squares. So the first term, the square root of the first term, the square root of the last term, and both of them have opposite sides. So we've gone from a polynomial with 4 terms to 3 sets of factors, and this gives us answers, right? So when y equals 0, x can be what for this one? Remember, we're looking for when y equals 0, so we factored all the way down. So if y equals 0, then one of these sections must be 0. So if the first section, x minus 2, we set every single one equal to 0 to find our solutions. Right? So for the first case, x is equal to 2. The second one, x is equal to 3. The third one, x is equal to negative 3. So if I had a graph, it would cross at negative 3, 2, and 3. I also know that it does what? It ends going up. It starts where? It ends going up. Why? Because the coefficient was positive, correct? It's 1x cubed. So it ends positive. It starts where?
Down.
Opposite of wherever it ends. So it starts down. I know it crosses at negative 3, 2, and 3. So I could sketch a graph like that. And that would be real close to what my graph would look like. Okay, so this is the end goal from all these numbers that we started with. The whole point is to find those solutions, be able to know what your graph looks like. Right? So in this one, I grouped the first two terms, I grouped the second two terms. Now you can also rearrange your terms. In this book, for this chapter, your terms are already going to be set together. But there are times where you can say, hey, the first and the third term are the things that have something in common, and my second and my fourth terms are the ones that have something in common. So they can be rearranged. But for this chapter, they'll all just be already together, okay? So in the first one, what do they have in common? They had 10x squared in common. So I took that out, and I got x plus 2. Well, that was super convenient because when I grouped the last terms, it was already x plus 2. Now, why would this be tricky if I'm taking out the x plus 2? What could you easily miss? This coefficient, right? So if I just took it out completely and said, oh, I'm going to factor out, and it's, so basically it was 10x squared times x plus 2. Is that the same answer? No. Because if you're like, if I'm just taking out, it's just 0. It's not there. It's not 0. There was a coefficient of 1. So we actually have 10x squared plus 1. There's a 1 here. And if you think about it, if you had a 0 there, always ask yourself, could I multiply that back and get back to where I was at? If you just had the 10x squared, you would be missing a bunch of terms. So always be willing to say, can I get back to where I was at? Is that correct on it? Okay. We talked a little bit about this. Some polynomials are quadratics in disguise. So 81x to the fourth minus 16, I just rewrote it as two square terms. So 9x squared minus 4 squared, and then this is a difference of squares. I know how to factor a difference of squares, so that was super easy. Just dropped it in. And then again, I have 9x squared minus 4, which is also a difference of squares. Okay, so again, we had another difference of squares, so we're factoring it out again. The whole point is to get down all the way to the end so that we can get x answers. So what would be our solution for this first binomial? X would equal what? When y equals 0, x equals what? We're setting this whole thing 2/3, correct. For this one, x could be
Negative 2/3.
negative 2/3. And then on this one, we would have to use roots, right? We could say 9x squared plus 4. We know we're asking the question when y equals 0. So I've got 9x squared equals negative 4. X squared equals negative 4/9. Now I'm going to take the square root of both sides. X is equal to, this one has an I, 2/3. Okay? We'd write it as 2I over 3. Because square root of 4 is 2, square root of 9 is 3. This has imaginary solutions. Those are no real solutions. These solutions won't matter in our graph. But we could actually put a point at 2/3 and negative 2/3, right? On the graph. It just means that the other place that it turns is not over the graph. Okay. So for this first example, we start with 6. I've got 6, 4, and 2. The very first thing that we're going to do is factor out anything that's is common. You never want to have a variable at the end. You always want to have a constant. Right? Because if it's going to be a difference of cubes or difference of squares, or if you're going to use the quadratic formula, you need to have a constant at the end. So I've already got a problem right here. I also prefer to always have a coefficient of 1 for my highest. So if I can get rid of this 4, that's going to make my life easier. So can we get rid of the 4? Can we get rid of the variable at the end? Yes, we were able to factor out 4x squared from everything. And we end up with x squared minus 5x, x to the fourth minus 5x squared plus 6. Again, this is a quadratic in disguise. I've rewritten it so that it's a variable squared minus just the variable and our constant. It just happens to be that our initial a term here is the actual x squared. So x squared squared minus 5 to the x squared plus 6. So now I can factor this just like x squared minus 5x plus 6. If I was factoring this, that doesn't look real intimidating, right? I would factor it and say it's x and x. What two values of 6 add up to be 5? What two factors of 6 add up to be 5? So 3 and 2, but they needed to be negative, so we're going to make them both negative. Okay. So in this case, that one's super easy. Now I just replace x with x squared. So I'm going to rewrite it as x squared minus 3 and x squared minus 2. So I took it out, made it look like a quadratic, factored it like a regular quadratic, because that was easy for me, and just plugged back in my value. Okay? So now we've got this 4x squared at the front. I've got my different factors. So what are my solutions? When this section equals 0, x equals what? 4x squared. We have to set every term equal to 0 to find a solution. So 4x squared equals 0. X would equal what? This is the easy breezy one. What does x have to equal?
2.
To equal 0. Anytime you have anything that is just all multiplied together, what does x have to be 0? 0. Right? X has to be 0 in this case. What is x in this one? X squared equals, we would have x squared minus 2 equals 0. So x squared equals 2. So for this one, x equals plus or minus the square root of 2. Right? Take the square root of both sides. X equals plus or minus square root of 2. So I've got two solutions there. So I've got x equals 0 for my first one, plus or minus square root of 2. In this case, what does x equal?
Plus or minus square root of 3.
X equals plus or minus the square root of 3. Move my 3 over because I'm setting the whole thing equal to 0. So now x squared equals 3, square root of both sides. So now I have 5 solutions. 1, 2, 3, 4, 5. My first one that I set it was a squared term. So actually I had 0 and 0. So I had 6 solutions. 1, 2, 3, 4, 5, 6. It says I can have 6 solutions. Right? Did we get 6 solutions? Yeah. So it all matches. Okay. So again, the goal is to solve for x. The goal is to get a solution for x. We're trying to find when x equals 0. We just can't do it. We can do it as long as we have a squared term, because we have those 4, we've got roots, factors, completing the square and quadratic formula, right, that we can all use to solve for x, to actually get x by himself. Remember, it goes all the way back to the beginning. X wants to go to the movies by himself. We just need to find a solution. We just can't do anything with him when we have higher forms, when we have more terms in there. So the whole goal is, how do I get this down to just 1x? Right? So in this case, I need to get x's all, we're asking those same questions at the very beginning. When x wants to go to the movies by himself, I need to get them all on the same side. So I move my 14x over, set the whole thing equal to 0. Well, I've got a problem. I've got a coefficient here, and I have a variable at the end. I don't want a variable at the end. We only want constants at the end. I'd prefer not to have a coefficient if I could get rid of it. Can I get rid of it? Yes. We can factor out the 2 and factor out the x and get x to the 4th minus 7x squared plus 12. This is a quadratic in disguise. I have 4 and 2 and 0. So I've rewritten it. We're basically What are we initially factoring? Okay, we're initially factoring x squared minus 7x plus 12. That's what we're doing. We're going to ignore what's in there. Okay, so can I factor this? Are there two terms, two factors of 12 that add up to be 7?
4 and 3.
4 and 3. Okay, but they have to be negative. Okay, so in this case, I could go, well, x equals 4 or x equals 3, but it wasn't x. It was x squared. So I'm going to replace my x with x squared. It was easier for me to factor it whenever it looked just like a quadratic. So I went ahead and factored it like a quadratic, and then I'm just replacing, I'm substituting back in. Okay. So what does x equal here? Can I do anything else with x squared minus 4? There's two ways to solve this one. It's a difference of squares, so I could go ahead and write it out like this, right? Or I could use roots and say x squared equals 4, and then do x equals plus or minus the square root of 4, which is 2. So x equals plus or minus 2. In this case, I got x equals 2, x equals negative 2. Did I get the same thing both ways? Yeah. Just sometimes if you know it's a difference of squares, it saves you some work. X squared minus 3, what is my x here? X squared equals 3, because I'm setting the whole thing equal to 0. So I have to move it over. So I've got x squared equals 3, so x equals plus or minus the square root of 3. Right? And then I have my 2x. 2x has to also have an opportunity to have 0. If 2x is equal to 0, then x equals 0. So I have 1, 2, 3, 4, 5 solutions. Am I allowed to have 5 solutions?
Yes.
Why?
Your original.
My original degree was 5. So I'm allowed to have 5 solutions. Right? There we go. Okay. So let's look at this one. How many possible solutions would this first one have? 3. It could have 3 possible solutions. How would we factor this one? What's the problem that the first step? Can I get rid of a coefficient? And is there a constant? Is there a constant here?
No.
No, there's no constant. So I need a constant, so what do I need to get rid of? The x squared. Okay? I have a coefficient for the first one. I'd prefer not to have it. Can I get rid of the 2?
Get rid of 2x squared.
Yeah. So I'm going to pull out 2x squared and be left with an x minus 3. Correct? So now, what are my solutions? If this whole thing is equal to 0, that means each of these parts have to be equal to 0. We're going to set each part equal to 0 to find our solutions. In the first case, x is equal to what?
0.
X is equal to 0. Plus or minus 0, technically. But it's 0, so there's 2. In this case, x equals 3. Okay? So I've got 0 and 3 as solutions. 1, 2, 3. Could I have 3? Yes. Could I have 3? Here's my solution. It's going to hit at the origin, and it's going to hit over there at 3. Okay? So let's look at this one. I've got negative 2x to the 6th equals 16. What's the first problem with this one?
You have to move 16 over.
Perfect. I need to move 16 over, or I need to move the negative 2. I prefer to get rid of my negative, so I'm going to go that way and have 2x to the 6th plus 16. Right? I'd prefer to not have a coefficient for my first one. Can I get rid of the coefficient? Yes, I can pull it out. So now I have x6 plus 8. Correct? Now, does this look like anything that maybe we could change it into? It's not. It's a cubed. Good job. So we're going to change the x to the 6 to the x squared cubed, right? Because I can break up this number into any of its factors. And then I'm going to have 2 cubed. Now, does this 2 go away? No, we can't. He doesn't disappear. Okay. So now I have a sum of cubes. So I have a binomial and a trinomial. We're going to take our first term, x squared, put it in all 3 spaces. We'll take our second term, put it in all 3 spaces. We know that for the trinomial, the first and the last space are squared. Now, I've got to deal with signs. All my numbers are in, now I've got to deal with signs. My sign of my original is positive, so the sign of my binomial has to be positive. My sign of my binomial is positive, and the sign of my trinomial has to be negative, and the last sign is always positive. Okay, so now I have 2. I don't lose that one. X squared plus 2. Now I have x to the 4th minus 2x squared plus 4. Okay, this is a quadratic in disguise. I've got 4, 2, and 0. Okay. I'm initially saying, are there any factors of 4 that add up to be 2? No, there's not. So I'm going to have to use the quadratic formula or completing the square to answer this one. Okay. But I also know that 2 equals 0. This one's going to give me an invalid solution. I've got x squared plus 2, so I could have x in this case would equal the square plus or minus the square root of negative 2. So this is not going to give me any valid solutions. So the only valid solution that I have an opportunity to have it from is down here. Okay. Could this have 0 solutions? Let's think about it. Let's evaluate it. From what we know, could it have no solutions, never cross the x-axis? What does the graph say? The negative 2 tells us what? It ends where?
Down.
It ends down. The 6 tells us what?
It's the same.
It's the same, so it also starts down. So could it have no solutions?
Yes.
Yeah, there's a possibility. And so far, I've got 2 is equal to 0, not a valid solution. X is equal to imaginary numbers, not valid solutions. And I've got to use the quadratic formula over here. So there's a good chance that there would end up being no valid solutions for this equation. All right? Okay, so that gets us through 6.4. If you already did 6.3, your homework this week will be the extra problems that we didn't do from 6.2 and then the 6.3, and then we'll have some for 6.4, okay? And then when we come back, we're going to revisit that synthetic division, or the synthetic substitution that we did, and we're going to use it for dividing polynomials.
Have a good Thanksgiving.